Hello and welcome back to BSG Webinars. I'm your host, Dan Carney. Whether this is your first webinar or you've watched them all, I'd like to thank you all for taking the time to join us today. Let's be clear on clarity. An overview on Seltzer Clarification is our 26th episode since the start of our webinar series. So if you haven't seen any of our webinars, please visit YouTube and search for BSG Craft. There you'll find all of our past webinars as well as great content from all our wonderful suppliers. So be sure to check them out. For future webinars, a link can be found on our homepage at bsgcraftbrewing.com and at bsgcanada.com. We also announce them in our newsletter, which is the best way to learn about new products and important information. So please sign up if you haven't already. You can also follow us on Instagram, Facebook, and LinkedIn, where we usually post daily. Next up, in 2 weeks, we'll have Blending In with Hop Solutions, presented by BSG's Eric Sannerud and Jason Hunziker of Stack Deck Brewing. The registration is currently on the webinar page located on our website, and we hope you can join us back here in 2 weeks. And then in today's webinar, Ashton will give us a presentation. We'll have a couple of polls peppered in there, so be sure to answer them. And then we'll open it up for questions. Please use the Q&A function for any questions, and we'll answer them as they come in. If we don't get to your questions today, we'll follow up as best as we can. We also encourage you to ask the best questions you can possibly, because we'll be selecting our favorite question and sending out a BSG swag care pack afterwards. So now that we have that out of the way, first I'd like to welcome back Ashton Lewis. Ashton joined BSG in December of 2016 and is currently BSG's Technical Support and Training Manager. Prior to working in the world of ingredients, Ashton was the Staff Master Brewer and Brewing Group Sales Manager for the Paul Mueller Company, living in the world of custom stainless steel. He was also a partner in the Springfield Brewing Company in Springfield, Missouri, and their master brewer for 21 years. Ashton holds a BS in Food Science from Virginia Tech and an MS in Food/Brewing Science from UC Davis. For the last 26 years, he's also worked for Brew Your Own magazine as a technical editor and Help Me, Mr. Wizard columnist. Thanks for coming back on with us, Ashton.
Thanks for having me.
And I'd also like to welcome Kane Escobar. Kane is brewer by education and trade with an immense passion for brewing and the brewing industry. After training in the quality department at Spetzel in Shiner, Texas, and finishing his BA in brewing from UC Davis, Kane began his 7-year career with Miller Coors, holding several positions such as analytical microbiological specialist, brewing quality specialist, and pilot brewer in both the Texas and Wisconsin facilities. As a pilot brewer, Kane worked on all the research and innovation projects for the entire Miller Coors network, including cider, flavored malt beverages, and seltzer innovation. In 2019, Kane took all his knowledge and experience in both big beer and running a pilot brewery to become the manager of research and brewing operations for RAR here in Minnesota, where he now operates the research brewery, performing all research and innovation for RAR and BSG. Well, thanks for coming back on with us, Kane. Happy to have you both back to talk all things seltzer.
Yeah, thanks for having me.
So let's get started. Ashton, I'll let you pull up the presentation so we can keep the webinar moving. And I will join you both for the Q&A afterwards.
Thank you for the nice intro, Dan, and welcome to all the people out there in the video land to join Kane and I to talk about clarity about seltzer. So the title of our talk today is Let's Be Clear on Clarity. And we've got kind of I think a fun lineup of topics here. Turn on my laser pointer. We have a combination of technical, kind of hypothetical theory on filtration and the practical side. So I assume everybody is here to talk about making seltzer clear. And this is a kind of a brief intro on what we're looking at here. Uh, this is what seltzer looks like after it's been fermented and shaken up. So, a lot of us have stainless steel fermenters. Hopefully, most commercial brewers have stainless steel fermenters, and oftentimes it's really difficult to know what the inside of a tank looks like. So at the end of fermentation, if these seltzer fermentations are mixed or roused, they tend to be a very milky white appearance, not really something that we would typically find in beer. So this is the type of beverage that we want to turn into, hopefully something that looks like water if the objective is to make clear seltzer, or if you're making a cloudy seltzer or a slight hazy seltzer, probably the objective is not to have it look the turbidity of unfiltered sake. So the agenda of today with our talk is that we're going to have a review of clarification methods that brewers routinely use, which also are used by other beverage producers. So we're going to kind of dig into the details on clarification methods and how they work. Go over some of the kind of the engineering principles behind clarification. So we're gonna cover the theory of clarification, and then we're going to end up with suggestions on the best route for clarity specific to seltzers. And then at the end of our presentation, we're going to have a Q&A. So just to echo what Dan said a few minutes ago, we're going to hold questions until the end. If you have questions during the presentation today, feel free to use the question feature to go ahead and type in your questions. Please do not use the chat feature because we want to keep all the questions under the question, but you can chat to other participants if you want to. So brief kind of a review of the goals of clarification in general for brewing and other beverage production. One goal is to perhaps remove microbiological things within the beverage if there are microbes to begin with. And certainly with beer and seltzer, we have yeast that we're going to be removing. So that's one of the primary goals. Another is the non-microbiological particles that are probably going to be in any beverage that you're clarifying, be it a non-alcoholic beverage or seltzer, beer, wine, cider. Fair amount of non-microbiological particles are in all those beverages, and in particular with beer, which we're all brewers, will be primarily proteins and polyphenols. I suppose there's some winemakers in the audience too, but for wine also, protein and polyphenol. But in seltzer, we don't, depending on the carbohydrate source being fermented, we probably don't have a lot of protein or polyphenol in our seltzer. So we're primarily going to be removing yeast and then other very small particles that contribute to light scattering and seltzer. Another objective of clarification in general is to promote physical stability and sometimes microstability. The latter is certainly true if we're using an absolute filter, like a membrane filter for sterile or for reduction of bacterial populations. And then finally, with some types of filtration, we might be aiming to have flavor refinement by removal of certain compounds that contribute to aroma and taste and the whole sensory profile of the product. So the first thing we're going to jump into here are types of clarification that rely on gravity. So this is a quote from actually a old friend of mine. Gravity never takes a day off, and I don't exactly know why my friend Jeff used to say that, but it probably had something to do with the propensity of falling down at times. So gravity never takes a day off, and we can apply that principle to clarification when it comes to gravity sedimentation. So what we're looking at right here, I don't want to really get into the details too much here, but it is an interesting principle. This is Stokes's law, and the Stokes equation, if you will, is a way of calculating the maximum velocity of a particle that's settling, and the characteristics of the particle that are of interest are the diameter. So that's a function of diameter squared. We've got the difference in density between the particle, in this case yeast, and the fluid that the particle is settling through. G is the gravitational constant, and then 18 is a constant, and mu is the fluid viscosity. So basically, if viscosity increases, sedimentation rate decreases, and diameter, particle density, the difference between the particle density and the fluid density, and gravity are all things that would tend to drive the velocity up. Now, of course, if we're on the planet Earth, our gravity is constant, so that's not a variable in this equation. It's just a constant. But the take-home message about gravity sedimentation is that it's reliable. Gravity doesn't take a day off. It's readily available, and it can be a bit slow. So here's an example of what we mean by a bit slow. We have two different cellars here showing horizontal lagering tanks. These lagering tanks here happen to be rather deep. These are approximately 10-foot tall tanks. You know, the diameter of the horizontal vessel is approximately 10 feet tall, and this vessel here is about a half meter in diameter. So we can calculate using the Stokes equation how fast a particle settles. So we can calculate the velocity of that settling particle, and then based on the velocity that we calculate and the diameter, we can calculate settling time. So in the case of these tanks here, these are actually chip tanks at one of the Anheuser-Busch breweries. In a chip tank that's about 10 feet diameter, we can calculate that based upon this particular yeast density, that it would take about 10 days for a particle to settle from the top of the horizontal tank down to the bottom. And if we look at a smaller tank, the velocity of settling is still the same, but we have a shorter distance to travel. So we have 1.7 days versus 10.3 days, same velocity. So the relevance of this is that it's relatively slow, but of course you can speed that up depending on the shape of the tank you have in your brewery. I just want to point out here that not all yeast density numbers that I could find in the literature are the same. There's actually kind of a range in this 1,100 kilogram per cubic meter is a typical density of a yeast cell. So if we're thinking about, how do we accelerate this? What can we do to speed things up? Well, one thought is to have a bigger yeast cell, which is this d squared factor, the diameter, to reduce the drag. There's less surface to volume ratio, and we're going to speed that up by making the yeast particle larger. So how would we go about doing that? Well, one would be through yeast selection to select for strains that are flocculent or that clump together after fermentation is complete. The other thought is to maybe select a cell that happens to be a little bit larger in diameter than others. So those are a couple ideas. And then the third option would be to perhaps add a fining agent or something to help clump the cells together at the end of the fermentation cycle.
There's one more I'll add in there, Ashton. Temperature will play a factor into that. So I know a lot of guys out there, they'll maybe crash their beers down to, let's say, 32 degrees, 30 degrees, whatever their glycol system can handle. So something like that we crash ours to 29 because that's going to promote more of those yeast cells clumping up. And if it's a beer, kind of, your proteins and polyphenols also tying into that. But just keep in mind that if you are dropping it to those lower temperatures, you have to understand what your overall ABV is on that product. So higher gravity brewing, you can get away with those 29 degree temps. If you have something that's more at a 5% brewed to strength, then you want to stay a little higher on that, just so you're not freezing your product.
That's a really good point on the not only changing the temperature to encourage flocculation, but also in the freezing, because some of the seltzers that our customers are brewing are brewed to strength, and some of these products are lower alcohol, and they have less carbohydrate to begin with in the liquid, so they're more prone to freezing than a beer. Yeah, it's interesting you mentioned temperature, Kane, because it's a negligible difference, but as temperature goes down, the viscosity goes up. So for the most part, temperature is a good thing because it makes the d squared value larger, but it also has an opposite effect on viscosity.
Kind of a way I like to look at the viscosity factor is think of it as a constant in your brand, because that's, if you're going from brand to brand, then you will, that viscosity factor is changing. But if that's your brand, then in theory your viscosity should be the same every time if you're hitting numbers, right?
That's a good point.
So
Yep.
so it almost acts as a constant.
Yeah, and it's also relatively small in comparison to the
Mhm.
D, because that's a squared, and that's what we're looking at here. If we double the size of the particle, if we go from a 1x particle, which the original example had an 8 micron particle, if we increase that particle size to a 16 micron, you can see what happens. We go from about a 10.3 day settling time, and we drop down to a 2.6 day settling time. And again, this is through that 10-foot column of liquid, or just a little bit over 3 meters. So the increase here is a 4x increase because we've doubled d, and d is squared. So the change in the particle diameter, the effective particle diameter by 2, has a 4x increase on the settling rate. Now the opposite happens too. We've got this blue line. So what is that blue line showing? Well, it's showing if we had a smaller diameter particle, instead of an 8 micron, let's say we have a 2 micron particle, or yeast cell in this particular case, what's going to happen to the settling rate? Well, it's going to go, that's a fourfold difference times, 4 squared is 16. So we see a 16 times reduction in settling rate. This 10.3 days goes to 165 days if we're relying on gravity. So there are some challenges with gravity, especially if we have small cells that don't tend to clump. And that's where findings come in. The findings that brewers can use for beer can also be used for seltzer. We have isinglass, which mainly the primary function of isinglass is to help increase the size of yeast flocks. We've got acidic polysaccharides, so-called auxiliary findings, products like Alginex and Chitosan, that are they complement, they enhance the effectiveness of isinglass findings like Magical or Biofine P19. So these auxiliary findings, they improve the function or the performance of isinglass, and they also help protein removal because they're charged to stick to proteins, which tend to have a positive charge, where yeast have a negative charge. So those are so-called auxiliary findings. These compounds can also be used in conjunction with silicic acid, which our silicic acid goes by the name Biofine Clear. So with silicic acid, we can also remove yeast and also chill proteins. So these are some options we have for findings of beer, and we can also use the same findings for seltzer. And again, the primary function of these findings for seltzer is to increase the flock size of the yeast. Do you have anything that you want to add to this, Kane, before I switch slides?
No, I think we're pretty good. Well, if I was to add something, it would be think of this process. It's cold break, right? So think of it just like you're hot breaking your kettle. What's happening there? You're adding findings to get the hot particles and proteins, polyphenols to coagulate and clump together, right? So they fall out of solution better in your whirlpool. Same concept here. I mean, we're getting all that material to come with larger particle size to help Stokes' law to be able to get that clarity out.
Yeah, and a lot of these work, like you said, with kettle findings. They really have a marketed effect on work clarity, and with the findings added to seltzer and beer, we can also have a pretty dramatic effect on clarity. So the kind of the take home on this whole gravity issue in the cellar is that time has value. If we look at the what goes on in the cellar, we're keeping liquid cold for some period of time, and with that, maintaining cold temperatures, we have an energy cost associated with keeping our liquid volume cold. That's part of the value of time. Probably argue that that's not huge if we have insulated tanks, or in this case, a nice traditional cellar underground. But where we really have a huge effect on the value of time is improved plant usage, where we're turning our tanks faster, which are of course not inexpensive. So we're turning our tanks over, we're getting product out the door, and we also have a very real effect on the cost of inventory and so-called work in process, or WIP, where we have money tied up in labor and money tied up in product that's just sitting around aging. So that's a real accounting cost that we're placing value on, and by decreasing that time, we making more profitable decisions for the operation. So this is a picture of some finding trials. And Kane, what are we looking at here?
So we did this kind of trial with a couple different yeast strains and tossed them in the Einhoff cones. And so you can see I can't really see the number. So number 14, so that would be our TY Pure. And this was just time, no findings. And just like lagers, if you age them long enough, you can get the particles to settle out, depending if there's anything else in there. And so why I wanted to present this is if you go to number 16 on the right-hand side, you see how there's still a haze. So you have to be mindful of your strain, the nutrients you're adding to your seltzers, and any other additives, because those may not clump to the yeast cells and fall out of solution. You may get a permanent haze carrying forward, where if you're just relying on sedimentation, you're going to run into issues and you're going to have a hazy product.
So just to clarify that, or no pun intended, but to repeat what you just said, Kane, the only difference among these three trials is yeast strain. The same
Yes.
nutrients and the substrate and everything were the same.
Correct.
Well, although we collaborated on this, we kind of did our own experiments. You work in a lab in a pilot facility, and I live in a home. So I did a home trial, and I'm a proud member of the MacGyver Club, and this is my home incubator. So this is actually a cardboard box on the top and another cardboard box on the bottom that I lined with styrofoam and put a muffin fan and a light bulb that I connected to a thermostat. So I fermented these in a controlled 75-degree environment. So I used the same liquid and the same yeast, and I split them into 4 different containers to run a finding trial. So this is actually what I got. This is the TY Pure as well, which you had in your clear sample, Kane. This is after 7 days of fermentation and gravity sedimentation at room temperature. So this is actually very, very bright. And then I decided to replicate what I think that some breweries do, is they either intentionally or inadvertently mix up the tank. In this case, I didn't blow the cone because I didn't have a cone to blow, but I mixed the yeast and the sediment back into the seltzers, and I used findings to see if I could clarify everything, because there's some non-yeast particles that settle to the bottom, and this is a typical sample that I pulled from my finding trials, and my trials actually did not result in a crystal clear product like I began with, which was kind of interesting. So the takeaway points about sedimentation is that gravity is reliable. Of course, it's available, but it can be slow. All hazes don't settle. There's some hazes that do not effectively settle out because either they're too small to settle in the production time that most of us have in our facilities, or they're so small that they actually don't settle. They're permanently like a sol. They're not in solution, but they're a particle that doesn't settle out. And then the other takeaway point here is that findings, they can remove just about everything that will reflect light or diffract light, but not all the time. So there are times that the findings will not settle everything out from a seltzer. So that kind of brings up the question: if our goal is to make a clear product, then what do we do? So we're going to go on to some other types of clarification. But first, we've got some live brewing news coming in. And we have a poll, and our poll here is: do you currently use findings to clarify some or all of your production? So again, we're asking, do you currently use findings to clarify some or all of your production? If you will, answer yes or no, and we will publish the results of the poll here live. Okay, so we had that question of like, what do we do now? Well, now we've got this. Here's the results for a poll. 86% of the audience, that's 18 people out of 21 responses, are currently using findings. We've got only 14%, or 3 of the total, who are currently not using finings. So that was kind of probably a expected result. We do know that finings are quite popular with brewers these days. So the other thought is more gravity. You know, if you've got if you look at the difference in gravity between the Earth and the Moon, the Moon has a less gravitational force than the Earth. But what about if we could increase the gravity and speed up the sedimentation? Well, of course we can do that with the centrifuge. And with the centrifuge, we increase gravity by taking advantage of the angular acceleration that occurs when a particle or a body is spun on a radius. So this is representing a shaft, if you will, an axis, and we're spinning on that axis, and there's a force exerted because of the angular acceleration that occurs. And we can convert that into so-called Z factor, which is the angular acceleration normalized to gravity. So if we have, so many times gravity, like in a fighter plane, so I think the fighter planes will pull like 10 Gs on some of the banks they make. So that's 10 times greater gravitational acceleration than the Earth's gravitational pull. So that's what a centrifuge does. My divider line here got moved around, but I'm gonna jump to a pretty cool video that shows. Let's go back out. Can you see the video now?
Yep, we're good. Thank you.
Okay. Yep. Thank you. So where I was before, here's our feed liquid coming in, and the clarified beer goes to the center and it flows out the top. And what we can see here is this accumulation of solids, and the blue at the bottom is the water that's actually holding the bowl shut. So we'll see in a moment that the water is drained and the bowl opens, and it automatically discharges, which is what's being shown now. This actually blows out, and on a large separator, these things kind of explode. They sound like a shotgun when they go off. So that's how a centrifuge works. Pretty simple operation, but there's a lot of precision parts, and these machines move around pretty rapidly. So they can be kind of scary if they get off balance. So that's the only video I have. Now we do have an example here of what happens as far as the acceleration goes. So in this particular case, we've got a radius of 0.2 meters. That's the effective spinning radius. So 0.2 meters is only 6.5 inches, not a whole lot of distance there. It's spinning at 5,000 RPM, which is a speed. And you can see that our Z factor is 5,600 times gravity. So 5,600 Gs is substantial increase in gravity. And if we look at the distance between these stacks, 0.4 millimeters is a common, pretty typical stack separation. And with this V max of 0.02 meters per second, our settling time is only 0.02 seconds. So really, really, really fast settling. So what are we looking at here, Kane?
This is the centrifuge here at the brewery. And so when we first installed, that's your stack of discs being pulled out. Now, as Ashton mentioned, you're talking about 0.02 to 04, or excuse me, 0.3 to 0.4 millimeters between each gap. So the idea is, think of your geometry of your tank, right? You have a shallower distance. You're having a faster increase in time of sedimentation, right? Well, this is essentially a lot of little tanks, if you kind of want to think of it that way, that are extremely small, 0.3, 0.4. So your sedimentation, that's why it's so fast, because that distance is so short. Now you can kind of see on the right-hand side of the degrees, your particles kind of starting to go up, and then it looks like they're swinging back down. So those are the G-forces, the G-force being applied, and so they're starting to get taken up and then go back out and collect in your discharge pockets. But what happens is when those pockets start getting full, then where are the particles going to go? Up towards the clear liquid. So that's why those discharges must occur, and you time them right so you maintain clarity of the product actually coming out.
So with your machine, Kane, your separator, this is spinning at a constant rate, or do you have a? Are you
Yep.
varying the? Okay,
Nope. It's spinning at a constant rate, 9,200 RPMs.
and then you're controlling the flow rate through the machine to control the clarity coming out of it. Is that correct?
Yep. Yep. So we control the actual flow rate going in, and then based off a turbidity sensor on the out. And I mean, there's units that have turbidity sensors on the in and the out, but we're dialing it in with a little diaphragm valve to manipulate that flow rate. You do have to keep in mind though, with lower centrifuge feed rates and longer residency times, it's not always all good. You may be thinking, okay, well, if it's in there longer, it's getting more separation, my clarity is going to be increased. But you also have to worry about any shear stress that's being applied to these cells themselves. Generally, if you're doing a combination of sedimentation and centrifuging, then you don't want to centrifuge a product that's been sitting there for a while. Yeast autolyze, and they start getting a little more fragile. So then when they get that shear stress applied, they break apart, and those cell walls get carried over, and those actually can give you a permanent haze that is carried forward. That you have to use other methods to remove.
And if your flow rate through the machine is too slow, you build up heat as well, don't you?
You do get some temperature increases. Yep. Yeah, my recommendation would always be to have a trim cooler on the out, so that way you have cold beer running through, and then it may heat up a bit in the centrifuge, and then it cools back down as it goes to your tank.
And for your tanks, your tanks are relatively small, but your typical runtime on one of like the 6 hectoliter tank, how long does it take to run a batch through the centrifuge?
Product dependent. So if it's something we want a little hazy, then it's a lot faster. But I mean, since our tanks are so small, we're talking about 30-minute runs.
That's pretty cool. So the thing about gravity is that it's with the separator, it's a pretty heavy hammer. You've got a massive change in settling rate. It's the difference between gravity sedimentation with Earth's gravity versus a centrifuge is just night and day. The centrifuges are proven technology. I'm old enough to remember that when brewers started using centrifuges back in the late 80s and early 90s, that there were a lot of concerns about product quality, especially with DO pickup, and even some of the centrifuges back then. Brewers were really not aware of what Kane has talked about with shear stress or shear damage to yeast cell walls. And there were breweries that had some haze issues that were related to centrifugation. But now, 30 years later, it's a proven technology. They're available in a lot of different sizes, and it's what a lot of brewers want. The downside, though, is that centrifuges are not they're not what we would consider inexpensive, and they're really a substantial capital expenditure for the brewery, and they are definitely not required to make clear seltzer. So the reason we bring them up is that we're kind of presenting a talk here that covers all types of clarification, and the centrifuge is a gravity type. So
I guess
I'm sorry.
one add on to the centrifuge is you do have that initial capital cost, but usually the payback on those for product loss is pretty huge. I mean, sometimes you pay them back in less than a year. And I'm not promoting centrifuge sales or anything, but it's something to keep in mind when you're thinking of sedimentation alone. Is you're going to be dropping all that sediment out, right? So what are you also dropping out is product that could be ending up in your tap room. So something to keep on the back burner.
Well, you didn't know about our live brewing news today, Kane, because the live update here is that we're now selling centrifuges. We're going to take orders at the end of the presentation. But that's a joke. So the question is here, we're just kind of curious, for those of you in attendance, how many actually do currently have a centrifuge? Yes, no, or perhaps coming soon. So just to piggyback on the payback on these machines, they're really effective if you have really hoppy beers where your losses are high on not only beer but your hop usage is high because you have high beer losses. So the payback on centrifuges is pretty darn good. And not a surprise here, most people don't own centrifuges. So that's we're not shocked to learn that, and we appreciate the input. Okay, now we're going to cover. We're not going to try not to get too caught in the weeds on depth filtration because this can be kind of a deep subject. But there are a lot of different types of depth filtration in the brewery, and examples include water filtration, wort separation, and of course beer filtration. But in general, depth filtration is described as a tortuous path, and this is kind of a pictorial depiction of a tortuous path. And what happens is the particles that enter this labyrinth experience changes in the shape, and they can settle out. And it's important that if you are running a depth filter, you need to have non-turbulent flow. So all these filtration mechanisms we're looking at today assume non-turbulent flow. So um, if you're, like a fluid dynamic person, it'll be a low Reynolds number so that there's no turbulence and that the settling can actually happen. So with depth filtration in a brewery, one example that we're familiar with is the filter bed that forms in your mash tun or lauter tun, or even a mash filter will have some type of filter bed that sets up. And Henry Darcy was he's actually a hydrologist that described liquid flow through sand filters. So basically, what Darcy's law says is that Q, which is volumetric flow rate, is proportional to a K value, so-called Darcy's bed constant. So as a filter bed becomes looser, if you will, like this grain bed, the K value would go up because that's a property of the bed. A is the surface area. Delta P is the pressure differential across the bed. So as the delta P goes up, the flow rate goes up. Mu is our liquid viscosity. So as viscosity goes up, flow rate goes down. So for wort separation, which is what this is showing, that's why beta glucans are of interest. They also affect beer filtration, and then the bed depth, or L, slows down the flow rate. Now, the reason that I selected a picture of a grain bed here is that if you start running a pump and pulling a high differential pressure across the bed, according to Darcy, this is going to increase our flow rate, which is true. But as the bed compresses, which we all know will happen if you rip this pump open and started pumping to the kettle or recirculating really fast, we would suck the bed down and our flow would actually drop off. And what we're doing there is we're changing the bed constant. So the important thing to realize about Darcy is that this equation was originally written for water flow through sand filters, which are non-compressible. But in breweries, most of the filters that we use on the beer side have some compressibility. So the take-home brewery pointers are that bed changes as we can change the properties of the cake, which does occur during beer filtration. And more delta P can change K because brewery filter layers are usually compressible. So from jam turning up the delta P that more delta P is not usually required. Did you have anything to jump in on that, Kane? That's I know that's kind of a lot of stuff.
I think we're good on that.
Okay. Why don't you jump in here and talk about these different types of depth filters that are used in breweries?
Yeah, so I mean, I'm sure some of you have these in your breweries or are wanting them in the future. But D and perlite plate and frames, all these have pros and cons, right? So something for like a D, you have to worry about the product being a carcinogen and cleanup, things like that. But D kind of act in the same concept. It is compressible, right? So you could bind a filter. The idea is initiating a pre-coat onto a layer. Think of having a screen. You have a screen and you're adding a pre-coat. So you're essentially creating a thicker and thicker mesh. And as you add more powder and then you start adding body feed as your product is going through, that mesh is growing and growing, making more and more little channels for particles to get trapped. Now, as your delta P goes up, those channels are starting to fill up. So you're getting a slower flow rate potentially, unless you completely bind it and then you're SOL. But those filters are essentially you build upon them, so it keeps growing, depending on how much room you have in the filter itself. Whereas if you go at the center, horizontal lenticular, now that media is already bound. So your combination DE perlite, that media is in powder formation. You would have to create a slurry and dose that into your inline with the product. Now, the center, all that media is already bound in a cartridge. So there's no room for it to grow. So you can't build upon it. So once it's bound and those little pathways are blocked, it's done. Your filtration's done. So it's very, very important on all these to really focus on your differential pressure. And then your horizontal leaf, same concept as the combination DE filter. These come in vertical and horizontal formats, but you're building a cake on there, and that cake is your filter in essence. And based on the powders that you're adding, the combination of the powders and the density of the powder, so the more powder to slurry solution you're adding, those in essence filters get thicker and bigger and could filter out more product. So there are different grades of DE and perlites. So if you want a primary filtration off that same filter, you can also get a polished filtration off that same filter based on your powders that you're actually adding.
Yeah, these filters, this type of filter is actually pretty uncommon these days. This is a combi filter where the depth filtration with the DE or the perlite is in the first section, and then there's a dividing plate, and then there's a plate and plate section where you can have filter sheets put in. I like this kind of filter. I think these are great. The RTC has one of these where Kane operates, but a lot of younger brewers don't like this kind of filter because they're kind of a pain to use.
Yeah, so I'm against on Ashton on that one. So we originally had one of those units and we've retrofitted it and hacked off all the DE portion, and now it's only sheet filtration still with a divider plate, and you'll see that in another picture. The reason I personally don't like it, and I'm sure Ashton has his reasons on why he likes it, but depending on the size of the brewery, so especially some of you guys that are pretty small, mind you, these initial purchases for one of these is extremely through the roof. So they're very expensive, but they are tanks. You will not break them. But the bad thing is, one, cleanup. Some of those powders are very messy. They're also powders, so you will need respirator of some sort when handling those. The other portion is at a very, very small scale, you start running into iron pickup because of the powders, and you almost have to go into a pharmaceutical grade powder selection, which is very, very expensive to not have that. There are some tricks of the trade, certain acid additions that you can do into your slurries while you're making your body feed, but that's another issue you got to kind of keep on that back burner and really pay attention to if you're starting to see maybe elevated iron content in your product, or you're starting to pick it up sensorially, that it could be that powder system. So
yeah, totally on that. Yeah, we had problems with oxidation with this type of filter, and we switched from DE to perlite, and the use of perlite made a huge difference. But yeah, I agree with everything you said on that. You also have a centrifuge, which is kind of nice.
Mm-hmm.
But these filters here, this type of filter is much, much easier to use than either one of these. The downside to this type of filtration material is that it's a little bit higher cost on the media, but the equipment itself is much lower than these style of filters, and they're less labor to operate.
Exactly. Plus the loss is a lot less. So you'll see a heavier loss on the sheet filter style.
Yeah, because on a sheet filter, especially this type where you have a filter cake, you can't really blow this out with CO2. I mean, you can push this out with water, but then you have to have deaerated water. With this
Exactly.
filter, you can blow it out with gas, and then because the bell is completely evacuated with gas, there's not a whole lot of product loss. So this is your filter, Kane, at the RTC, and you said
Yep.
this is converted to, you only use the sheets on this.
Yeah. So we've retrofitted some of the stuff, and it looks a little different now than than it was there. But you can see kind of hanging out on one of the little plates. That's actually the big dividing plate. Yep. So we can run primary and polish filtration through a single pass. And so below it is actually a filter run we did with carbon sheet filters from Filtrox.
And whether you're using a plate and plate filter, which is what this is now, or if you're using a stacked lenticular, both of these types of filters allow you to use different filter media.
Yep.
And with a powder filter, you can use different grades of diatomaceous earth, which is what this shows with the different pore sizes in the diatoms. Or you can use different types of perlites to have different filtration effects. What's this gallery of stuff down here?
So the gallery stuff, that's actually part of our little Seltzer Palooza project. So those are all initial seltzer bases made with different sugar substrates. So everything from honey, cider, agave. The only one that didn't make it there that's still in process is our wine base. But these are all cleared up by sedimentation. So this is
like
this is about 7, 8, 9 days of sedimentation. What was that, Ashton?
Okay, so for the most part, these are all bright just by natural sedimentation.
Mm-hmm.
We're looking at 8, 9, and 10. What are your carbohydrate sources on these?
9 would be our cider, 10's our honey, and 8 would be 8 is the honey, 10 is the cider, and 9 is actually the Demerara sucrose.
Oh, cool.
Demerara, however you say it.
So that's an interesting thing that we're probably going to see more of this, where people are using different carbohydrate sources to get different flavors and aromas and colors from their ciders or from their seltzers.
Absolutely, and that'll be something you got to keep in consideration on how that substrate is going to react with sedimentation, because it may not clear up.
And that's these are those 2 yeasts that you had before AFCON cone
Yep.
trials.
Yep, and that 15 and 16 cone.
Mm-hmm. So a lot of stuff with media filtration and depth filtration. So the take homes on this is that, whether you have a beer filter or not, we all use depth filtration because we all, have a mash that we're working with. There's a really wide range of complexity and cost associated with depth filters. The simpler filters, especially the styles that use lenticular type cartridges, are the least costly up front, and the more complex systems with dosing tanks and dosing pumps and plates and frames get to be really quite expensive. In my opinion, I think that the depth filtration is a great complement to gravity clarification. So if you don't have product that's clear enough coming out of your fermenter and your post fermentation gravity step, whether it's gravity alone or gravity plus findings, or even with a centrifuge, you can use a depth filter to polish your product. You can use a depth filter for all your filtration needs. There's a lot of variability with the ease of use with these different products. They're pretty forgiving on the feed strength. So if you have a different clarity coming in, you can modulate how the units operate to handle different cloudy liquids with different flow rates and dosing rates for your filter powder if you're using powder type filters. So depth filtration, there's a lot of options out there and a lot of flexibility. So this is our last poll question, and the poll question here is, if you have a filter, are you using and you can actually use a couple different options here. DE perlite, so that would be a powder filter, a combination, which would be combination DE perlite and sheet, or you can just have a sheet filter if you want to answer it like that, cartridge filter, or you don't have a filter. So the cartridge would be like a lenticular type filter setup. Wow. I expected most brewers not to have filters, but I did not expect 82% of the attendees not to have filter systems. So again, that is consistent with what we're seeing on a lot of the questions that we get from y'all out in the field on these seltzer products. So the last thing, I'm going to briefly just kind of blow through this because these are really not relevant to seltzer filtration. There's a whole type of filtration or sieving that we use in breweries that range from the macroscopic to the microscopic. And I just wanted to throw some of these out. We've got different screens that are used. These are inline screens that have limited usefulness, but they're really effective if you need to protect a nozzle or a spray ball or whatever. If you don't want to have big particles or nuts and bolts or things that would be considered maybe abnormal in your piping system because they don't really have any ability to hold solids. But a similar type filter would be a filter screen, which I love these in front of heat exchangers to prevent hot particles and so forth from entering a work cooler. This is an inline strainer that's similar to these screens, but it's easy to remove and take out the element. So this type of screen is actually quite useful. And then this is a bag filter or a sock filter arrangement where you can put different types of elements in a filter housing. This one here is actually an industrial. I don't think this is would be considered a sanitary design, but there are a lot of different types of bag filter options out there.
Yeah, and those bag filters are good on the back side of things as well. So if you're doing your blending and moving product around, if you're adding maybe preservatives that haven't fully dissolved, that could kind of be a saving grace on you from those solids moving to a different tank or to packaging. And for kind of like the mesh gasketed filters, as Ashton said, those do have like limited holding power. But I know I've seen this in the industry where brewers are making seltzers and they're cutting the bags open of sucrose or dextrose, and bags make it into or little particles from the bags make it into the kettle. Those can kind of save you from having those particles enter your heat exchanger and get lodged in.
Yeah,
or even your fermenter.
Yeah, there's a lot of neat stuff out in the world of sanitary components that a lot of times brewers don't even think of using because they're not really designed for breweries. There's a lot of cool stuff for the dairy industry, prevent parts of milking operations or maybe cattle hair or whatever from getting into the milk. But these are some more examples of surface filtration. This is a cross flow filter. So in this case, there would be a membrane and you're flowing across the membrane, and there's definitely a back pressure here to, give the liquid a reason to flow through the membrane. So there's a back pressure on the end of it, but there's flowing across, and the flow across keeps the solids, in this case yeast, from accumulating on the surface. And this is a lot different than a so-called dead end or perpendicular type flow where you're flowing right into the membrane. And an example of that in a brewery would be if you're using like a sterile filter to filter a product, whether it's seltzer or beer, and you've got yeast or other, let's say, carbohydrates or gums, beta glucan or whatever, proteins that can gum up the membrane, you can easily blind a filter that's operating in a dead end or so-called perpendicular flow. So that's one of the real advantages of a cross flow filter. Here's some other membrane type filters. This is an RO cartridge. You can see how it's wound up. These are pretty cool for water treatment. And this is not real common in breweries. This is a hollow fiber polymer where you actually kind of flow through a straw, and the liquid, the permeate, will flow through the membrane of the fiber, and then the retentate, where the solids are, flows out the end of it. But these are actually fairly common in wine, and in beer we see cross flow filtration systems like this that use ceramic rigid cartridges, and there's some breweries use that for removing waste beer from waste yeast to concentrate yeast streams, and a lot of interesting technologies on cross flow. But for a lot of smaller breweries, we've got a couple of things here that are good talking points. What are we looking at here, Kane?
So the big blue BWS cylinder, that's a carbon filter. So that actually so this whole system is a RRO system for the brewery. So it supplies all our treated water into our hot liquor and cold liquor tank. So city water flows through the carbon filter, goes through the carbon filter, and then it goes into a pre-filter, which is on the left-hand side right next to the flow meter.
Left-hand side next to the flow.
Keep going. Keep going. Down.
Oh, right there. Okay.
There we go.
Little guy.
So it gets filtered through the carbon bed, then goes through a small pre-filter to catch any particulates that may have passed through. And then it goes through the RO membrane system. And then from there, it does a discharge and then sends water to our hot and cold liquor tank. Now, this same technology is currently being used in seltzer production, but it's very expensive because of the initial cost. So you're seeing it out of some of your larger players who have the capital expense to buy a unit like this. They're very time consuming and expensive to operate, but think of it this way, you're running your water in there to strip everything out, right? So if you're running a seltzer product, you're pretty much stripping everything out besides your water and your alcohol. So, and then the large tower, that's actually tied to a skid that's through the window. That's our deaeration unit, our all docs. So that makes all our deaerated carbonated water for the brewery. That's used for packing lines, cutting product, pushing dissolved oxygen out of our filters.
So when you're making seltzer, you're making high gravity seltzer, and you're using this deaerated water for cutting.
Yep.
So a lot of surface filters that are used in breweries, a lot of it's on the utility size. So surface filters, kind of a summary here: defined pore size. They're considered absolute filters. They either go or they don't go. So like if you're trying to put a particle that's too large through a surface filter, it's either going to fit or it's not going to fit. And if it doesn't fit and there's sufficient concentration of the stuff that doesn't fit, it'll clog up your filter, because a surface filter has effectively zero sludge capacity. The ones that are dead end, cross flows are different, but most of these membrane filters don't have a sludge capacity. In other words, they don't really hold solids and they easily blind up. That's when they're operated incorrectly. Usually there's a lot of protection in front of a membrane. They're relatively easy to operate. You have to protect them to prolong service life. That's with so-called guard filters or pre-filters. And they do work very well for seltzer. If you have a clear seltzer stream and you want to use sterile filtration or membrane filtration, they do work quite well, but you just have to have a relatively clean stream to present the filter with. So the key summary points here to our presentation, and we've got summary points and then some thoughts on how to best clarify seltzer. So if we go through gravity clarification and findings and look at their strengths, there's the real strengths is that there's no special equipment required, easy, simple process, and gravity is always on your side. The downside is that some hazes simply don't easily fine. Findings are very, very well suited for certain particles, but not so well suited for others. And then there's the real small particles that simply may not settle in any kind of reasonable time. And then it's hard to set a clock by sedimentation. In other words, it's hard to manage a plant if your clarification time is variable. Centrifugation, they work great, versatile, improve efficiency. Possible weaknesses are the expense up front. They might not produce brilliant clarity. In fact, a lot of breweries that produce brilliant beer with centrifuges only will either have multiple, like two centrifuges in line, or maybe even run the beer twice through it, or some just run a lot slower. But it's not uncommon to put a filter behind a separator. And then the other disadvantage could be a DO pickup, but this varies a lot by the machine design. So the newer machines are known for low DO pickup when they're used properly. Depth filter, you can use alone or after gravity methods. There's a lot of options with depth filtration, pretty wide range of cost and complexity. I think the major downside of depth filtration is challenging to operate, DO pickup, as Kay mentioned earlier, potential pickup from your filter aids if you're using DE or perlite of certain grades. And then the effluent and waste streams are very real on how to deal with your the waste side of a depth filter. And then finally, there's surface filtration. I would just generally say that these are not real common for smaller brewery applications because they tend to be kind of designed for larger, more specific applications that require a certain amount of volume to justify.
There's one thing I do want to add that I forgot to mention earlier. When you're looking at kind of depth filtration, surface filtration, is absolute and nominal. So you may see that on a cartridge, or your supplier may say, "Oh yeah, it's an absolute filter." Because for depth filtration, because it's a lot of little channels, and the absolute that's what it is. If it's 0.45 microns absolute, then you have a sterile filter on your hands right there. That is the smallest that it'll filter out. It's 0.45. If it's a nominal, then it's almost like an average, okay? Because you may still have pass through of those larger particles, but it's not 100%.
And one of those, that's a really good point, Kane, because with a nominal filter type, if you're running your flow rate at a higher flow per filter area, you can end up blowing material through the filter. And I kind of glossed over that earlier when I said that these are all based upon laminar flow or non-turbulent flow. So if you have a really high flow rate through a depth filter, depth filters are not designed for laminar for turbulent flow. They're designed for a really smooth, low velocity flow. So if the velocity through the filter is too high, then the filter basically quits working. So it's important to have enough area for the flow. So this is the take home, and this will be our last slide, and we'll get into the Q&A. The first take home is that gravity plus findings may or may not work. In Kane's trials at the RTC and my trials at home, we both showed that you can produce brilliant product without any filtration at all. But then we both demonstrated, in Kane's case, with using different yeast strains, and in my case, for doing something that's probably atypical, where I intentionally mixed up the vessel after fermentation. We both demonstrated that the gravity may not work. So sometimes it does, sometimes it doesn't. The real take home here, I mean, this is the point that I'm in sales, so I'm going to put my sales hat on here. I think the best process for consistent, reliable production is a combination of methods. And I'm not trying to sell you any product. I'm trying to sell an idea here. But I think if you're running a brewery that you want to have consistent product coming out the back door, that you're really probably best served with, relying on gravity, maybe using some findings, but then also do something on the tail end to clarify your product. And even if your product is sometimes clear and sometimes it's not, if you put something on the back end, after your gravity is done, you have the ability of producing a reliable and consistent product in a given time frame where you can, let's say your process is a 10-day process, you can set your clock by it. It's always 10 days versus, 10 days this time and 3.5 weeks another time.
Absolutely. It comes down to how costly is your time? How much is your time worth? Because if you're shaving off days and adding some consistency to your schedule, and that has huge ripples.
Yeah, especially like if you've got distributor orders and now your production is variable because you're not sure that you can get your production out the door in time, or even if you're a tap room brewery and you run out of product, what's the lost revenue because you ran out of product. So that's kind of the sales pitch on having something to be able to clarify your product. So that kind of, with that one statement, I think that kind of wraps it up. But I do want to make sure that we have plenty of time for Q&A. So um, on behalf of BSG and the Roar Eagle Brewery, I'm going to thank y'all for your attendance, and hopefully we've got some good, lively Q&A here that we can follow up with.
Well, thank you guys. Yeah, let's jump right into the Q&A. Again, if you have any questions, just direct them through the Q&A function, and we'll answer them as they come in. Also, after the webinar, we'll select the best question and give away a BSG swag pack to one of the lucky winners. So please ask away. So let's get started here. First question that came in is, if I carbonate in a fermenter, how and when do I add the finings?
Ashton, do you want this one, or do you want me to?
Let's both answer it. You go first, and I'll see if I have a different answer.
Okay, so I kind of look at this in the standpoint as if I was doing it, right? So if I was doing this, I would either inject my solution of findings via a corny keg or one of those open top Sankey kegs. I would inject that in prior to carbonating, mix my tank so you get full distribution of it and have it all homogenized. And then from there, let it settle, rack it off. And then if you are carbonating through your racking arm, then obviously rack that out your racking arm and then attach your carbonating stone and carbonate that way.
Yeah, the only thing I would add to that is you're probably implying this, but make sure you blow your cone and purge as much sediment before you start that whole process. So to follow up though,
crash cool it, right?
Crash cool it, yeah. So remove the sediment from the bottom, have your beer cold or your seltzer cold, run through a recirc loop, inject in line. So if you look on our website has a lot of information on how to use our different products, but if you look at the suggested usage of all of our findings, the best way to use findings is to actually mix them in line. So if you're transferring from one tank to the other, you would want to do an inline injection, but for most small operations, that's not done. So the recirculation method and inline injection works quite well.
Excellent. All right, next question is, currently I am using barley and dextrose to make seltzer because I'm still a bit confused on flavored malt beverage, FMB laws. Maybe this could be a lecture in the future, but so I'm also trying to remove color as well as haze in the same process. Any thoughts on that?
Can I ask one question before we answer that question? Jack, are you located in the United States or in another country? And let's just assume Kane for the time being, he's in the US.
United States. Yep.
Okay. I know you know the answer to this one, Kane, so you jump on it.
Okay, so obviously filtration is critical here. If you want to remove color, you're kind of limited on what you can do. So carbon would be your best play, unless you have a big checkbook and you want to buy a fancy system as far as like vacuum distillation and RO filtration. But best play would be carbon filter. You can get that in either immobilized carbon, so in the form of a cartridge, like the lenticular cartridges, or the sheet filters. The other option is loose carbon, which is very, very messy. You're gonna have to be wearing a respirator, but that's pretty much your only play for stripping color on a budget. And in doing that, to get your filtration is, so it's kind of a you need a pre-filter. There's no way around it, because you're going to get more life out of that cartridge if you have a pre-filter than if you just hit it with your maybe just sedimented product. You're going to get less reactivity going on. So if you hit it with a pre-filter, you'll get that initial clarity, and then the carbon will also bind some more particles, plus it'll give you that stripping action.
Now, as far as the whole TTB and FMBs and state laws, I doubt we'll ever have a presentation about the legal side, because there's so many variables. We're a national company, and we're not in the business of giving legal advice. We're not attorneys, and we're not consultants when it comes to tax law. But what I will say is that not all states have the same rules. So there's some states that you don't have to use malt, because the TTB actually doesn't require malt for certain beverages. So you can use 100% sugar as long as you're complying by the TTB regulations. I don't want to stick my neck out and giving you any wrong advice on what the specifics are, but you don't have to use malt for seltzer. But there are some states that say that they have rules that are different than the TTB federal laws. So there is state to state variability on what's permissible and what's not.
And if you're classifying as a flavored malt beverage.
Yeah. All right. Let's move
versus beer.
Yeah. Let's move to the next question. Can you use all the mentioned findings, Magical, Biofine, P019, Algenex, and Biofine Clear, in the seltzer brewing process altogether?
You can. A couple of those products are kind of redundant. The Magical and Biofine P19 are both isinglass or collagen products. So one thing to point out on that is that, for a lot of our customers, they're very conscientious on everybody who consumes their product. So that the truth is that collagen and isinglass are very, very effective finings, but they're not vegan. So the popularity of those products has really gone down in the last several years. And then the Algenex and the Chitosan type products, those are acidic polysaccharides, and those are auxiliary finings. So you can use an auxiliary fining in addition to an isinglass or a collagen type product. Those would be used in conjunction. And you can even use Biofine Clear silicic acid in conjunction with isinglass, and you can also use the acidic polysaccharides in conjunction with silicic acid. So silicic acid can actually be used in conjunction with isinglass, but it can also be used with the auxiliary finings.
Ashton, you outlined that in your presentation, didn't you? You had them kind of broken down.
There is a chart on that, yeah. So this presentation will definitely be available for review.
Yep. So yeah, that presentation will actually come in an email a couple days later, probably via Zoom. So keep an eye out for that if you want to download the presentation. So, all right, next question. With the goals of both clarity and flavor reduction in mind, could you expand on the advantages of carbon treatment / filtration for seltzer, GAC additions, and or sheet filtration?
So I mean, the simplest one is a cleaner product. You're gonna have some organic aromatics being produced during fermentation, and kind of bound to your yeast. And when by filtering, you're pretty much pulling all that out that's coming from the yeast itself. And the carbon filtration is the cherry on the top that's kind of finding any other organics that could be perceived unsatisfactory aromas and characteristics.
All right.
And what was the second part?
The second part was GAC additions and or sheet filtration.
As far as
can you expand on the advantages of carbon treatment / filtration for seltzer? So with the goals of both clarity and flavor reduction in mind.
Sure. I mean, your sheet filter is just another tool. I mean, it's filtration and carbon treatment, and you have the option to do both with that one system.
Mm-hmm. Yeah, I think for the benefit of others, I think the GAC that's been referred to as granulated activated carbon. So if you're using something, to Kane's point earlier, if you're using carbon to remove flavor or color, you need to protect your carbon because the carbon is very reactive. And if there's junk and if there's background noise that you haven't removed, you can shorten the life of your carbon. So you need to, pre-filter with a sheet filter or a depth filter or something to clean it up before you present the seltzer onto the carbon.
Plus, think about your operators too. I mean, it's not a nice product to be dealing with in a powder form. So,
all right. Next question is: we made a seltzer with TY48. It worked well for attenuation, but cleared up very slowly. Do you have any recommendations on yeast?
TY Pure.
Yeah.
Yep.
I mean, so Ashton actually had a chart in the presentation. The blue line that took 165 days. So TY48 actually has a smaller yeast cell size. So that's why you're kind of struggling with getting it to settle out.
Well, we have a link in the chat section. Also, you can find it on our website. So, so next question. We made a beautiful base and noticed certain flavors from our flavor house added significant haze back to the product. Normally the citrus flavors. Anything we can do besides changing flavor houses? We do biofine and use a centrifuge and add flavor in the BBT, obviously before packaging.
No, you're kind of SOL on that one. That's when you got to throw back at your flavor houses and see if they can, if you don't want to change flavor houses, see if your flavor houses can optimize the flavor for you and pull out whatever substance is causing that haze in the product itself. Yeah, I've also seen it in my experience getting that through pasteurization. So I'm not sure if you guys are pasteurized or anything, but I've seen kind of a haze just pop up with pasteurization, or it'll come up in the flavor add and then disappear with pasteurization. So I've seen that as well.
All right, thank you.
I got to put up my sales hat. So we have a whole range of carry citrus flavors at BSG that are. I mean, I have a lot of customers that have used them before. I have never heard of that problem with carry products. So I think it depends on what's in the citrus, and if it's a purified oil, that's different than a citrus product that might have juice or other compounds in it. So they're I think the key to all this, though, Kane showed a lot of trials that were on the bench, and even my little home experiment was on the bench. Your question said that you had a beautiful base, and then you had a reaction with what you added to it. That really just reiterates how important it is to run bench trials. If you have a clean base, just to play with it on the bench. That way you don't end up sacrificing an entire batch.
Absolutely, especially if you're adding other things such as acids and preservatives.
Mm-hmm.
Know the way they should be added and what can be mixed with what, because you'll find out very, very quickly on a bench trial if that's a no-no of what you're doing, and instead of wasting it on a large scale batch.
Yeah, good point. All right. Next question. Stone Fisher, he first off says, "Hey guys, thanks for the discussion. When utilizing the time gravity while serving from BBT tanks, do you suggest adding findings in kettle and I'm assuming fermentation vessel or kettle plus serving tank?"
Well, I think it depends on what I'm thinking this is about seltzer, so we're not really
Yeah, my first
thinking
thought was
much of,
substrate.
yeah, if we're just talking sugar water. But if you're in one of those states where you're using some malt, then I can see adding findings in the kettle if you have a malt constituent. But for the most part, um, if you read the CFR, the Code of Federal Regulations on the use of a lot of clarifiers and findings are used for beer, a lot of the clarifiers and finding agents really are supposed to be removed before you serve. So I think it's important to understand what you're actually using to clarify your beer or seltzer, and to determine if there's any removal required before serving. But for the most part, you want to have your clarification occur prior to bringing your product into a BBT.
Yeah. So, two more questions. So this one is actually one I've always personally thought as well. Does the average consumer really care that much about color? Any surveys or studies? And I assume like color and clarity, because there's some very popular seltzers out there that I know a lot of brewer friends and stuff get really excited about, and there is thick as orange juice. So, or your hazy IPAs. And so, I don't know if you guys have ever heard, Kane, especially some of your background with, Miller Coors and stuff, if there's any surveys or studies done on that.
There are some. I'm sure there's tons of surveys and studies, and you'll probably find a couple that are public access. The rest you'll probably have to pay for them, but it depends on your market, right? It depends on demographic, location. So there's a lot of other little key things into answering that question. The demographic the target market for the States is going to be different than say Europe, let's say Canada. So I guess know your customers.
Yeah,
Now, my standpoint, whether people like it or not, is hazy is lazy. So I like crystal clear product, but that's just me. I'm one little cog in the whole system.
I'll jump on the other side of that one. I do prefer clear products, but I like hazy things, and I think that are there surveys? Absolutely, and there's surveys on everything. Um, Depending on the size of your operation, the survey could be, you know, you get a group of people at the end of the bar and you say, "What do you think about this product?" I mean, that is a type of survey. But if you look at non-alcoholic beverages, when I was a kid back in the '80s, there was a hugely popular drink called Orange Gino, which was awesome. It was like, I don't know, like maybe 3 or 4% orange juice and carbonated water, and it was in this really cool bottle, and it was cloudy as all get out, and it was a great product. So I think if you own the haze and you're able to sell the haze, you can use the haze and the color as a form of authenticity. If you drink, again, when I was a kid, you drank concentrated orange juice products and they were clear. Well, real orange juice is not clear. So now the not from concentrate juices, the supply, the producers of those things, they look at the stability of the cloud and all the optical measures that go into that. So I think that haze can be a real positive thing if you do it correctly.
Yeah, one of my favorite seltzers out there. It's a prickly pear guava flavor, and I mean, you couldn't shine a light through it, but it's fantastic. And so, and they bill it as that. It is a hazy IPA. And
Sure.
one of the questions, on top of Eric's original question was, you know, isn't hazy seltzer a current selling point? Which I think it is, just like brewing IPAs, like you have an hazy IPA and they sell like crazy. They have a great markup, and they're good for breweries, cash flow. So I would never be opposed to telling someone like, don't create a hazy IPA or a hazy seltzer for that matter. And I know like everyone has their opinion, but I also, if I'm out on a boat on a lake, I probably don't want that hazy seltzer. I want that crisp, clear, light-bodied seltzer. So it goes both ways, really.
I think my feed into that is absolutely the haze trend is out there. It has a place in the market, but do it right. Understand that it's not just taking the bottom pool off the cone of the tank, and here's our hazy product. And the yeast, is your haze coming from an ingredient? Is it coming from the yeast itself? Is it coming from a cloudifier that you're adding to get that haze? And then understand the shelf life of those materials that you're putting in there, because what's happening to the yeast, it's starting to autolyze, right? So you're getting some nasty components, nasty flavors that you don't want long term by having that yeast settle out and die in there. Or it may be a certain ingredient that is hazy turns clear after a certain time. I've seen that happen before. So really understand what you're doing in a sense of ingredients, and if it's going to be hazy, then just do it right.
Right. All right, let's move on to our last question, which is more of a broad question. What is the size difference of yeast between, say, ale and lager yeast? Which is larger?
I don't have a general answer to that question. Do you, Kane?
Uh, from my experience, what I've seen, ales are larger. I guess I mean it must yeah, I don't know. There's so many yeast strains out there being modified and everything. I'm sure there's been a crossover.
But in general, would you agree that whether you're looking at lager or ale, we're probably somewhere in the 7.5 to 12 micron range for most brewing strains?
Yeah, probably.
And then some of the, like you said, the TY48, we know that cell size is about 2 micron, which is really quite a lot different than a typical brewing strain. And the question that just came up is yeast size something we see on a spec sheet? I can't remember seeing that at all. And the answer is no. That's typically not something that's on a spec sheet. And if you do have a microscope, you there are ways to you can get a microscope that has a scale on a slide, and you can look at basically a ruler under a microscope. But you can also use the grid on a hemocytometer or other cells that are in your field of view as kind of references. But if you use a microscope a lot, especially hemocytometers, you'll kind of learn to recognize the general sizes of cells that you're going to see in your field of view, and you could pull in some of these things because the numbers that we showed earlier, the Stokes law on the sedimentation rate. I mean, to be honest, that was kind of fun to calculate those numbers because I don't see those calculations actually. A lot of times you see them as a reference of, well, we can use Stokes law as a description of settling, but when you crunch the numbers, it's like, wow, this is you can really get some real data. So the answer to that question is no. We don't see cell size listed, and we don't see cell density listed either. And that's like I said, I used 1,100 kilos per cubic meter. And if you look at the literature, there's a range of densities out there for yeast cells.
And don't be scared to ask your yeast suppliers. I mean, a lot of them are very very open, and they'll gladly give you that information.
Yeah, absolutely. All right. Well, that's all we have time for today, guys. Also, everyone, just keep an eye out for an email in a couple days that'll have links to this webinar, PDF version of the presentation, and some other fun links to click on. If you have any other questions, please feel free to email us at info@bsgcraft.com, and we can connect you with Ashton and Kane and help you in any way we can. So, also like to remind you that past webinars are on YouTube. And remember to look for new episodes, like our Hop Solutions episode in 2 weeks at this time. You can find the link on our homepage, BSG's newsletter, social media channels, or just ask your customer sales representative, and anyone can help you out here at BSG. So, again, I'd like to thank you both, Ashton and Kane. And I'd also like to especially thank our audience for your support by tuning in here and watching some of the YouTube videos. So, guys, it's a pleasure. I hope we can do it again. I know we will probably do it again. So, everyone stay tuned. We'll have more information on seltzer creation.
Hey, one shout out though. I'm double vaccinated, and CBC is being held this year. So hopefully the next time we see some of y'all, we'll actually see you in person, and maybe we can have a cold seltzer or a beer together. So hope to see y'all in Denver, and let's keep on pushing to get our lives back together.
Yep, we'll definitely be there. I do a lot of planning for it, and I know we've already reached out for some of the beers, so we'll have a lot of great selection. So stop by our booth.
Party.
Not trying to make a plug here, but Ashton got me a little. So, all right. Well, from all of us here at BSG and RAR, cheers everyone, and thanks for joining us.
Take care.
Bye-bye.